Hey kids, welcome to class 123. So there was like an issue with the first video I made of this, so I had to like do it again. And then I did the second video, got to the end, and I was like, you know what? There's a better way I could do this. So then this is my third time doing this. So forgive me if I skip through or move a little bit too quickly, but there is a slow down button on YouTube. Like you can make the lesson slower by half speed. Which also means you could actually speed it up. So if you don't want this video to be as long, you can listen at 1.5 times speed or maybe even double speed. Just an idea. I listen to stuff at 1.25 speed. Maybe those of you who listen to podcasts or audiobooks know this already, though. So anyway, we're going to talk about voltage and current in series and parallel circuits. So just quick reminders. A parallel circuit is this one on the left here. Current has some choices. Current leaves the battery, and it can go down this path here. So that loop, it can go down this loop here, or it can go down this loop here. At the end of the day, though, it all recombines and goes into the back end of the battery. But there are choices in a parallel circuit, multiple paths or branches, as I'm going to refer to them. Series circuit, not so much. Series circuit, just one loop. Okay? There you have it. Just one way for the current to go, no options. So what I want you to do is open up this FET simulation. This is slightly different than other ones we've used before for circuits. Now you're going to click on Intro. And here's why it's slightly different, and I just kind of had to mention it here. It's slightly different because in this simulation, the ammeter isn't a part of the circuit like it really should be. It's kind of just like a probe where you could check the current at different points. Why am I doing this? Because today I'm interested in looking at the current at different points in a circuit, not so much with how a circuit should actually be set up in real life. Okay? So, there's a time and a place for everything. I think this is the place to just use the probe ammeter. You'll see how that works in a second. So you're going to make these two circuits. Please don't skip on making the circuits. I think just the act of making circuits helps you with this topic, okay? If you're skipping out and actually making the circuits and just looking at me do them, you're really not getting as much out of this topic as you could. So this parallel circuit here has a 9-volt battery, 5 ohm resistor, 10 ohm resistor, and 15 ohm resistor. The order doesn't actually matter, but that's the way I'm doing it. Just keep it simple. How do you change it? You just click on them when you make it, and you change the resistance. This is a series circuit, same battery, 9 volts, and 5, 10, and 15 ohms. Again, the order doesn't really matter, but if you want to just do it like mine, you could do it that way. So here's what it looks like once you got it. Something like this. All right, I'm going to put the voltmeter and the ammeter away for a second. So we have some current going. We have conventional current. We have some values. Looks pretty good. Someone asked me the other day, what's a resistor? It's basically just a thing that slows down current. Light bulbs act like resistors. Any electronic equipment acts as a resistor. So someone said, why do you want to slow current down? Well, think about it. Every piece of electronic equipment needs different current going through it to work properly. If you have one thing that needs 2 amps and another thing that needs 1 amp, you need to make sure the current that's going through those two things is different. How do you do that? This is kind of, hand waving a little bit, but you use some resistors to change the amount of current going in different directions. Right? We'll get, again, more into that when we get to more complicated circuits. So what do I ask you? What's the first thing I ask you to do? First thing I say is don't measure anything. What do you notice about the current through the battery? And I mean the battery through each circuit. So let's look here. We take our ammeter, and then you could take this little probe here and look at the current here. Oh, we're not measuring, right? So just look at it. So if I look on the left-hand side, the battery in the parallel circuit, current's going pretty fast. If I look on the right-hand side, the series circuit, current's going pretty slow. So what I see right now is that current is greater in the parallel circuit. So I is current, greater in parallel circuit. All right. We sometimes refer to this as the total or equivalent current, okay? The amount going through the battery frequently, and especially in the AP exam, that most of you obviously aren't taking that, they refer to the current through the battery. That's like the total current through the system, or the equivalent current, if you will. All right. Now actually, let's take a second to think about this. If the current is greater in the parallel circuit, what does that tell you about the total resistance in the parallel circuit? The resistance in the parallel circuit has to be lower, right? That's interesting. It's made up of the same resistors as the series circuit. How does it have a lower resistance? Well, that's actually for another class. Today, we're just going to focus on some of the basics, all right? Just keep that in the back of your head. These are the questions and the things you should be thinking about. If the current is greater in the parallel circuit, it must have less resistance. All right, so now use the ammeter to measure the current through the batteries. How does it differ? Now we're going to get the ammeter out. Current through the battery in the series is 0.3. And this one is 3.33. So parallel is 3.33. Series is 0.3. So our prediction, or what we saw, was accurate. Okay, so let's write that down. Current series equals 0.3 amps. Current parallel equals 3.3 amps. Why don't we write these values down on our picture here? So I'll make this one. This was 0.3 amps. And this one is 3.3 amps, just to kind of bookkeep a little bit. All right, so let's talk about current in series and parallel circuits in general. So make an observation about the current in the series circuit versus the current in the parallel circuit. What does that mean exactly? I don't know. Just literally just look at it. Just play around. That's what we would be doing if we were in class right now. So just playing around with it. Let's see. Let's look at the series circuit first. Okay, so the current through the battery is 0.3. The current through this wire over here is 0.3. There's 0.3. That kind of makes sense. They're on the other sides of the battery. So look at the current through this resistor on the right. 0.3. Okay, this one, 0.3. Okay, the current is 0.3 everywhere in a series circuit. That's interesting. Now, it's only 0.3 because of this specific circuit and those values. So let's just say the current is the same everywhere in a series circuit. So I is same everywhere in series circuit. By the way, I forgot to mention before, if you didn't print this out, I would highly recommend you at least sketch this picture as best you can, just to take good notes. Now let's look at a parallel circuit. Is it the same everywhere? I don't know. Let's see. So let's take this probe. So this is 3.3. Okay, so what's the current here? 3.3, 3.3. This is a junction, so it's kind of got a split, right? Maybe like 1.65 each way. Okay, not quite. But it does split. Okay, 1.8 goes this way, 1.5 goes this way, and that's dictated by the resistors. So 1.5 goes this way, it splits again, 0.6 and 0.9. So let's look. So we have 3.3, 1.8, 0.9, 0.6. Why don't we add those all up? 1.8 plus 0.9, that's 2.7. Plus 0.6, that's 3.3. So, oh, that's interesting. So all the currents through each branch adds up to the current through the battery. That kind of makes sense, right? I mean, it's the junction rule, right, in action. So current through each branch in parallel adds up to total current. Now, so the current is the same everywhere in a series circuit, and in a parallel circuit, the current in each branch adds up to the total current. I wish we didn't have to memorize that. Oh, wait, you don't. This is physics. You don't really have to memorize anything. You have a reference table. Look at the very bottom here. I don't want to reveal everything. That's why I'm looking at the very, very bottom. It says series circuits and parallel circuits. Notice series circuit. It says I equals I1 equals I2 equals I3, and so on. Parallel, I equals I1 plus I2 plus I3, and so on. So in a series circuit, current is the same everywhere. In a parallel circuit, it all adds together to one big current. All right? So let's write that down. Series, I equals I1 plus I2 plus I3, dot, dot, dot. In parallel, like we said, parallel, it all adds up. I just made a mistake. Hopefully you noticed it. I made that mistake on purpose to see who's paying attention. In a series circuit, all the currents are equal, right? In a parallel circuit, that's where they add up. You gotta pay attention, guys. All right. So the current is blank in a series circuit. The same everywhere. All right, the current through each resistor blank, the total current in a parallel circuit adds up to, So the current through each resistor adds up to the total current in a parallel circuit. This would work for light bulbs too, by the way, if I replaced all those resistors with light bulbs. On your diagram on the first page, fill in the current values for each resistor as well as the batteries. So we did it for the batteries. We said that was the same everywhere here. So this was 0.3 amps. This was 0.3 amps. This was 0.3 amps. I don't remember what these are, but I'm going to see if I can. This was 1.8 amps. This was 0.9 amps. And this was 0.6 amps. Does that add up to... Yeah, it does. And hopefully you kind of see a trend here, and there are proportions here. We'll talk about this more next class. But notice how, like, the one on the left here, the 5 ohm, has half of the resistance as the 10 ohm. So half the resistance, less through twice as much current. And it has 1/3 of the current, or excuse me, 1/3 of the resistance of the 15 ohm resistor. That's letting through 3 times as much current. So that's kind of how this stuff works. It makes sense. Okay, that's something I want to emphasize. It's intuitive. It's logical. But again, we'll talk more about that in next class. All right. So make some observations about the voltage drop across each resistor in the parallel circuit versus the series circuit. So let's check that out right now. So we're going to put that away for a second. We're going to take out our voltmeter. So if I want to check the voltage, let's just check the voltage of the battery. So the voltage of, oops, hey now. Voltage, this battery here, 9 volts. That makes sense. It's a 9 volt battery. If you switch these to the other terminals, it would be negative, but we're not going to do that. All right, so let's check the voltage here. The voltage across this resistor here is 4.5 volts. What about this one here? 3 volts. What about this one here? 1.5 volts. Okay, so it's different. The voltage drop is different across each resistor. And that's something we should expect in a series circuit. So but hopefully you notice it all added up to 9. So voltage in series across each resistor adds up to the battery voltage. So let's see if the same goes in a parallel circuit. In a parallel circuit, let's explore. So the voltage across the battery is 9 volts. Hopefully I don't have to show you that, but I will. Let's look across each resistor. 9 volts, okay. Let's check across the other one. Sorry, it's hard to do this. That's 9 volts also. Let's check across this one. That's 9 volts also. So the voltage across each resistor in parallel is the same as the battery. So voltage in parallel across each resistor is the same as the battery voltage. Now, circuits get much more complicated with this. There's compound circuits that are series and parallel mixed together. But for now, we're just looking at the basics. So where does this appear on our reference table? Look at the next one. So now it's kind of switched. In a series circuit, current is the same everywhere. In a parallel circuit, voltage is the same everywhere, or across each object at least. All right? So, in series, V equals V1 plus V2 plus V3 plus dot dot dot. In parallel, so series is where they all add up now for voltage. In parallel, voltage is the same across each. So this is not something you need to memorize. It's actually not even really an equation. I would say it's more of a concept that's on your reference table. So it tells you the concept there. All right, so just to sum this up, the voltage drop across each resistor, blank the total voltage of the battery in a series circuit. So the voltage drop across each resistor adds up to the total voltage of the battery in a series circuit. And the voltage drop across each resistor, blank the voltage of the battery in a parallel circuit. So the voltage drop across each resistor is equal to the voltage of the battery in the parallel circuit. On the diagram, on the first page, fill in the voltage values next to each resistor. So we knew the voltage here. Okay. So we said the voltage here was 9 volts, 9 volts, and 9 volts. Okay, because in parallel, voltage is the same. in parallel, current adds up to the total current. In series, current is the same everywhere, but the voltage is what adds up to the total voltage. So we have a 9-volt battery. I think we said this was 4.5 volts. Just double checking my math here. Yeah, this was 3 volts, and this was 1.5 volts. All right. So just double checking all my math here. All right. So that looks good. Now, we didn't do math here. We just kind of used a simulation. What we're going to start doing soon is we're going to start doing this stuff without using the simulation, and you're going to have to solve for it mathematically. But we're going to explore that more next class. All right. So here's your exit ticket down here. This picture is not on the Google form, so you have to make sure you watch this video to see it. So it says you need to see the video for this. It should say these questions, or this question, these questions. You must upload a picture of your work / answers. So you're going to upload a picture of this, okay, everything in part D for your Google form, okay? So I give you some info. We have a parallel circuit here, and we have a series circuit here. I give you the voltage of that battery, okay? I forgot to write that this is, we need to know this. This is an unknown here. Okay, so I give you the voltage of this battery and the current through it. You have to give me the voltage across these two resistors and the current through each resistor. Over here, you don't have to give me the resistance of anything. Over here, I give you the voltage of the battery, and I give you the voltage across this bottom resistor here and the current through this top resistor. You need to fill in the rest. Okay, if you have any questions, stop into Extra Help tomorrow at 3:15.